All right, in this question, we're going to answer a lot more questions. And so this one is a little more of the types of questions you're going to run into on your exam. Table 10.3, this table down here at the bottom, shows the age in years and the retail value in thousands of dollars of a random sample of 10 automobiles of the same make and model. We want to do several things. We want to construct the scatter diagram. We want to compute the linear correlation coefficient R and interpret its value in the context of our problem. We want to compute the least squares regression line and plot it on the scatter diagram. We want to interpret the meaning of the slope of the least squares regression line in the context of our problem. We want to suppose that a 4-year-old automobile of this make and model is selected at random and use the regression equation to predict its retail value. And then we want to suppose a 20-year-old automobile of this make and model is selected at random and use the regression equation to predict its retail value and interpret the result. And then we want to comment on the validity of using the regression equation to predict the price of a brand new automobile of this make and model. Okay, so let's first begin with constructing the scatter diagram. Now, all that really means is we are going to plot the x and the y values on an x and y axis, and we only need to be within the first quadrant since all of our values are positive. So here's our scatter plot drawn on a nice grid. You might use graph paper or something like that, but we're just plotting each individual point. And notice it looks like just a collection of points. We might notice, though, that we could probably draw a line going right through those points right in here somewhere. So it does look like it's linear in fashion, although our points are further away than they were in our last example. All right, so we've got our scatter plot right there. Let's continue with the other stuff that we wanted to do. Well, we want to compute the linear correlation coefficient R. And we did do that before in our last section. So let me show you how I've moved the data into Excel, and recall that we used R squared to find our correlation coefficient. So our y's go first. In the case of correlation, it doesn't really make a whole lot of difference which one we put in first, but let's put in our y's. So our first one is in slot B1, and then our last one is B10. Oops. And then my x's is A1 position to A10. Oops. And it gives me a correlation. Now remember, this is R squared, so the next thing we want to do is take the square root of 0.670248, and that will tell us what R. Okay, so when we take that square root, we get 0.8, and I'm going to go ahead and put R is 0.818. I'll round off to 4 decimal places, 7. All right, now, remember, the closer a R value, this coefficient is to 1, the better our linear correlation is. Okay, so correlation is. I knew I was saying something strange there. All right, so the correlation here is pretty strong. So we're just going to say this is a decently strong correlation. Okay, it's not extremely strong like a 0.9 would be, but it's a pretty strong linear correlation, and I probably should say linear. Okay, so there's our interpretation of that R value. Now, the next thing it asked us for was to find our least squares regression line. So let's first begin with the slope. So we're going to say equal slope. And again, we want to put in y values first. B1 is the very first one, down to B10. And x values will be A1 down to A10. And there's our slope. And we did see that it should have been a negative slope when we looked at the scatter plot. All of the points were going downward. And that makes sense. These cars are depreciating over time. All right, and then our y-intercept, let's just hit equal, intercept. And again, I'll just hit let's do the y values first, B1 to B10. and A1 to A10. And that gives me 32.83. So our equation, y hat, is going to be negative 2.05x plus 32.83. Okay, now we want to graph this thing. All right, now I want you to recall how to graph a line back from algebra. The first thing we do is we locate 32.83 on the y-axis, and we plot that on the y-axis. So here on the scatter plot, notice that, well, 32.3 somewhere in here, all right? And then my slope is negative 2.05, so I want to go down 2, or down 2.05, and over 1, which would put me right in there. And then I was able from that point and that point right there to draw the line. And of course, I've done this graphically right here within the Word document so that it looks nicer. Okay, and you can, of course, let some computer program graph for you if you like. All right, we can see, of course, that it's going through 2 of the points, or it's very close to 2 of the points, not quite on, and then others are a little more scattered about our line. All right, so we've got our least squares regression line plotted on the scatter diagram. Now let's interpret the meaning of the slope of the least squares regression line in the context of this problem. Our slope was negative 2.05. All right, well, let's just notice our data here for a minute. You go back. Our x values is the age of these automobiles, and the y value is how much they're worth. So negative 2.05 means essentially that our y values are age, or rather our value of our car is going down by 2.05, which is really 2,000 per x value, per year, since this is measured in year. So our interpretation of our slope is that the value decreases by 2,000 for each year that goes by with this car. All right, so let's take a look at 5. Suppose a 4-year-old automobile of this make and model is selected at random. We want to use the regression equation to predict its retail value. So all we're going to do, since 4 is the year, that's our x value, we're going to go to our equation that we had, and let me move this over, and we're going to plug a 4 in for x here. So we're going to do y equal negative 2.05 times 4 plus 32.83. And we're going to get the answer to that. Oops, except I can't type. And that gives us 24.63. So we can expect that a 4-year-old vehicle is going to be about $24,630 in value at that point. All right, now I don't know what it was to begin with, but obviously close to our y-intercept of 32,000, or almost 33,000. All right, so our next question is to do, I believe, the same thing for 20 years. So let's see. Yes, we want to suppose that a 20-year-old automobile of this make and model is selected at random. All right, so let's do exactly the same calculation. And then we're going to talk a little bit about this one, though. It's a little bit different. We'll see why. And if we do that calculation, we get negative 8.17. Now, clearly, we are not going to give away the car and give somebody $8,000 with that car, which would be what a negative value would indicate. However, 20 years is a long time, and let's notice that our data, if we go back to it, only includes the years 2 through 6 of this vehicle. It is a bad statistical practice to try and predict things outside of the range of the original data. So if we're trying to predict anything outside of the range of 2 to 6 years, we are really making a prediction that's not a valid one and does not give us good information. So it's not wise to use this regression equation for years outside the original range. Original range of time. Okay, so that's called extrapolation, just so you know what that word is, and it is just not a good thing to do. All right, now let's go back, because we have a couple more things we need to do. We needed to comment on the validity of using the regression equation to predict the price of a brand new automobile of this make and model. Well, again, we've got that same problem that we had in question 6. It's outside the range of our data. So it's not a good idea. It's extrapolating. However, it is a little closer to our range. So certainly it's not going to be as invalid as going out 20 years. But again, you can probably say if you've owned your own vehicle that that first year the value goes down dramatically from the moment you drive off the lot. So it's really not valid unless we had 0 as one of our values here to help us figure out what that would actually be. So we are not going to predict that value. We're just going to say that it's not very valid. It's outside the range of our data.